All right, let's get started with today's material. So, starting chapter 6 this time, chapter 6 now is a lot like chapter 4 was. Chapter 4 was applications of derivatives. Chapter 6 is going to be applications of integrals. Now, I lied to you early on, and I said an integral is basically an area. And that was a lie. We need to adjust our thinking now to start thinking about an integral as an infinite sum of infinitesimals, of infinitely small things, kind of. That's the intuition we need to develop. And we used integrals to calculate areas, but we can use integrals to calculate all sorts of things, not just areas. So let's see quickly some of the ways we've already been using integrals. So I've got some curve here, doing whatever it does. We'll say this is the point B on the x-axis, this is the point A on the y-axis, or this makes more sense to put the A here and the B here. We could use an integral to calculate this area. And there's two ways that we could think about it. So we think about the area is the infinite sum of all the infinitesimal areas. You integrate dA and you get your area. And you can calculate those arbitrarily small areas however you want. And we talked about two ways that we could do it. So take some point here on the curve that has the coordinates x comma y. We could slice up this area into intervals this way. And so here would be one of our little dAs that we're adding up. That infinitesimal little rectangle right there, right? And what is the area of that infinitesimal thing right there? Well, how do you calculate the area? What's the area of a rectangle?
Base times height.
Base times height. And so in this case, we were doing the area of, what's the height of this?
It's y.
It's just y. And then what's the width of this little thing right there? It's just a dx. If you're slicing this up, then your infinitesimal small slices in the x direction is what we mean by dx. And here's how you've been calculating most integrals. To do a very concrete example, really quick, if we just took a curve that was going down, we'll say this is y is equal to 1 minus x, just a line slanting down. And we were trying to calculate this area. This is going from 0 to 1, right?
Yeah.
What is that area? That's the integral from 0 to 1 of what?
1 minus x.
Of y times dx. Now y in this case is 1 minus x. Right? But that's what you were doing. You were doing this exact thinking.
Yeah.
I need you to start thinking about it more general like this rather than just thinking about plugging your function. Because another way we could have done this is I could have taken my slices this way.
Yeah.
And so for my caked slice here, for this slice, it would have been looking like that. In that case, if we did our slices that way, what would the area have been? So one way we thought about it is if we slice up in the x direction, we would have been doing the integral from 0 to a. But we could have also done the integral from 0 to b, taking our slices this way.
Okay.
Right?
Yeah.
And now, what is our base of our rectangle?
dy. Y. Or x, my bad.
X. It's the distance from here to here. That's what the x coordinate is. So it's x times dy this time. That's the exact same thing. So you can calculate it, doing it y dx and doing the infinite sum that way, or doing x dy and doing your infinite sum that way.
Yeah.
So that's one way we've been using integrals to talk about areas. We've also used integrals to get displacements from velocity. Again, if I have some random velocity function here, for all, v of t, and I want to get, if this is my velocity from some time interval starting at 0 going to some time a here, and I want to get my overall displacement, what do? I break it up into these little infinitesimal displacements. So here's my little teeny ds, if we're using s as our displacement function, is what we usually use, right? Here's a little ds, and what is this little ds? How do you calculate it? What is the area of this rectangle. What's its height?
Height is
It's whatever our function is, v of t.
oh, yeah.
And what's the width here? If this is our t,
Delta is
dt. Not a delta t now, a dt.
Yeah. Oh.
And that's exactly how you get displacement. Think about it. So ds here, we're saying is equal to vt, v at t, times dt. dt is the little width here that we have for it.
Yeah.
An infinitesimally small width, but a little width we have here. And the height is the velocity. And what is a velocity times a time? It's a displacement. And so we got an arbitrarily small, a little infinitesimal displacement here. You calculate all those infinitesimally small displacements and you get your total displacement. S of t is equal to that integral. Right?
Yep.
Or in other words, s is equal to the integral of all your little ds's. This is what I need you to get comfortable with, thinking about it that way. So today, we're now going to be using integrals to solve volumes. And so the way we're going to do it is our volume is equal to the integral of all our little infinitesimal volumes. And we're going to do an infinite sum of arbitrarily small volumes. Okay? So let's look at some generic picture for a second here. We're going to be in trouble with my art skills, but we'll try it the best we can. So I've got some figure here, whatever it is. I'm trying to make it look the same on the top and the bottom. So sides are straight down. And we want to calculate the volume of the sink.
It's a closed top, right?
Yeah, closed top. Flat surface, closed top. So this comes around, whatever like that, right?
Yeah.
And let's put our XYZ system in here really quick. Here's X, here's Y, here's Z, there's a figure. Some height up in the air, little a, and it goes all the way up to some height B. Some figure.
Yeah.
You with me? Now, how do we calculate the volume of a figure like this?
Use rectangular prisms.
Area of the base times the height is in general how you do this, right?
Yeah.
So if I could somehow get the area of this sink, the area there, and then I can multiply it by its height, and that would give me the overall volume,
Yeah.
right?
Yeah.
And that would be pretty straightforward.
Well, what if it's a shape that doesn't have a straight up and down height?
Right, so that's where we're going to get in trouble now, is what if our shape isn't straight up and down, and instead the area constantly changes as our height changes? Right, so now what if it's a figure that looks something like this? Now that formula doesn't work anymore.
Yeah.
And that's a much, much more difficult problem to deal with. Right?
Yeah.
Yeah.
And so, if we can somehow find what we call the cross-sectional area at any height, so like some slice of this ink, trying to make this look somewhat decent, I take some slice of this ink right here. Let's say the cross-sectional area of that is, let's say we can figure out the function that gives us a cross-sectional area for any height z you want.
Okay.
You with me?
Yeah.
Then our volume, how are we going to get the volume? Our volume is going to be the integral from A to B of all of those slices. I need to take that slice and I need to give it some infinitesimally small thickness. And then if I add up all my slices that are infinitesimally small from A to B, then I'm going to get back my volume.
That's true.
You with me?
Yeah.
So my volume is going to be my cross-sectional area at some point times what? What's the thickness of that going to be?
Infinitesimally small.
So what symbols do I write?
D.
We're going in the z direction this time, sorry. I erased my z. So dz. Now I could have just as easily had this thing flipped on its side this way and found the cross-sectional area at any x and multiplied it by a dx.
Could you do dy then?
Yeah, I could have also flipped it this way, and how I put my coordinate system here is completely arbitrary.
Oh.
I can pick whatever coordinate system I want. That doesn't change my figure. But this is going to be the idea. Find some cross-sectional area, multiply it by an infinitesimally small width or thickness, and then add up all those cross-sectional little slices. and that will give you the overall volume. Make sense?
What happens if you have a different shape on the bottom than the top?
It's fine as long as, so it doesn't matter if this is the same as that, as long as I can come up with some function such that I can get the cross-sectional area at any point.
And how do you do that?
Well, you're going to have to somehow get that from the problem. It's like if I gave you this and you're saying, how do you get the area under this curve? Well, you have to know what the curve is, then you can do it.
Gotcha.
You have to somehow have information such that you can figure out the cross-sectional area at any point, then you can do the problem.
Okay.
So you'll always be given problems where you can calculate the cross-sectional area.
Instead of approaching it like slices of a cross-sectional area, could we do like rectangular prisms? Is that like, it's like, instead of rectangle?
The reason that you wouldn't use, are you thinking like a rectangular prism being both really skinny and really thin, but tall?
Yeah.
So the reason that you wouldn't do that is because then you'd have both a dx and a dy, or both a dy and a dz. You'd be doing it arbitrarily small in two directions, and we don't know how to do integrals like that yet. What you're thinking is a perfectly valid way to think about it, and this would be a concept that comes up in Calc 3.
Okay.
Oh, so it is a real thing.
It is a real thing, and there are ways to think about problems that way.
Okay.
But since we only know how to work with an integral with respect to one variable, we're always going to be taking our slices along one particular dimension, and then figuring out the cross-sectional areas as we change in that dimension.
So I guess you could do the same thing for any dimensional shape. You can find the area for your cross section. If you're trying to take the volume of like a four-dimensional shape, you could do it. I presume.
Yeah. And so, again, that would be a Calc 3 thing. All right, so let's do our first problem. A pyramid has a height of 3 and a base of 3 meters. Okay. So we're going to find the volume of some pyramid. See if I can draw this somewhat decent. So we've got some pyramid. The pyramid has a height of 3 meters, and its base here is 3 meters, and the distance from here back is 3 meters.
Is that Z?
Well, we haven't put any coordinate systems on this thing yet. We're just trying to find the volume of the sink. Now, I'm going to inject some coordinate system on the sink. Here's how I'm going to inject the coordinate system. There's an infinite number of ways to solve this problem. There isn't the right way. You pick the coordinate system you want to use to solve the problem. There's more clever ways of picking your coordinate system and less clever ways, and it will help save you some algebra. But there isn't the right way to do the problem. So I'm going to pick a coordinate system. Here's the way I'm going to do it. I'm going to make my x. Let me first try drawing the prism. This really helps if I can do at least a half decent drawing. We're in trouble. Have to make the base. So, sharp. Okay. Okay, not ideal, but I think you see it.
Yeah.
Yeah.
I'm going to make my coordinate system so that here's my y going through it and coming out the center right here. This is my x, and then my z is coming out this way, something like that. You with me?
Yeah.
Now, it's really hard to work with these things drawn three-dimensionally. So I'm going to redraw this as though we perfectly line it up so we can only see 2 dimensions of it and can't see its thickness. So I'm going to redraw the problem in a way that's easier to work with. So the z is coming directly out of the board.
Yeah.
And so now it just looks like this. Right? I turn it on its side so that z is coming perfectly out of the board. And now it just looks like this, looking at it perfectly on the side.
Yeah.
I can't see any of its base, can't see nothing. There it is, our pyramid. You with me?
Yes.
Now I need to calculate the volume of the sink. Right?
Yeah.
So I'm going to take my slices here in the x direction. Now what is a slice of this thing going to look like?
Square.
A square. Right?
Yeah.
No, I drew it bad. It has a square base. 3 meters by 3 meters. Right?
Yeah.
So when I take a slice here, that slice is going to be a square.
Okay.
So let's think about my area at, first off, let's do it at a concrete point. If I have it drawn this way, what is my area at 3 equal to? What's my area at the base?
9.
What's my area at the base of the pyramid?
Oh,
9 meters squared.
This is going down 3 meters, we would have gotten 9. How did you get that? You did 3 times 3. What would my area be if I went 1 meter down on the sink?
3. Say 4 meters squared.
If I just went 1 meter down?
Oh, 1 meter squared.
8? No.
If I cut this pyramid right here, 1 meter down, and I take off that piece I cut off and look at its base, what is the area of its base?
5 meters. Or just gonna be 3.
Where are you getting these numbers? So the bottom, you get that this thing has a square bottom, right?
Yeah.
So the bottom of the whole pyramid, the area of its bottom is 3 by 3 meters, or in other words, 9 meters.
Yeah.
If that's going all the way down 3 meters to the bottom, what if I cut this thing 1 meter down?
Then the base would be 1 meter.
What is the distance from here to here?
1 meter.
1.
1 meter.
Okay.
It's 1/3 of whatever that was, because we took 1/3 of the pyramid.
Oh, yeah. Okay.
And what is this distance right here?
1/3. Or
1 meter.
1 meter. And so what is the area 1 meter down?
1 meter.
1.
1 squared, or 1. But so the area at 1 was just 1 squared. What is the area 2 meters down?
4. It's gonna be
4.
yeah 4.
Yeah, 2 meters squared. And in general, what is my area if I go down some distance x equal to? Just x squared. Now what is my area if I go down 8 meters? Is it 64?
No, you don't have it.
No. So we have our bounds. It only goes from 0 to 3. And so the area that I'm looking for here, our area is the integral of all my little dA's, but I'm going from 0 to 3, slicing it in the x direction here,
Yeah.
Okay.
right?
Yeah.
And that little area, so now, sorry, not my area, my volume, is all these dV's, infinitesimally small volumes. What is the volume now of this little slice right here? It's the area of the slice times the thickness.
Which is dx.
What's the thickness?
Really
If this
small.
is the x direction. Well, what are our symbols for?
The integral.
dx. That's what dx means.
Oh, yeah.
An infinitesimally small displacement in, look, your delta x is a change in x.
Yeah.
The way that we start thinking about dx is an arbitrarily small change in x. This is some change in x, this is some arbitrarily small change in x. And so the thickness of that isn't a delta x anymore, it's a dx.
Okay.
So you take the area, multiply it by its thickness, and that gives you the volume of that little slice. And we're going to take all those volumes starting at 0, take all those slices all the way up to 3, and we're adding them all up as we go.
Yeah.
So we're slicing this up an infinite number of times, and we're doing that infinite sum. That's what the integral is doing for us.
Okay.
Make sense? So our volume then is the integral from 0 to 3 of our dV here is the area function times our thickness. Our area function is x squared times dx. And now this is trivial. 100%, the hardest part of these problems is setting them up, understanding the scenario, coming up with some way of graphing it, and interpreting the integral that corresponds to it. After that, these problems become easy. So now let's take the integral. What's the integral of x squared?
2x.
X squared.
X cubed over 3 plus 1 divide. And now we need to evaluate that from 0 to 3. Plug in 3, what do you get?
9.
9. Plug in 0, doesn't matter, so it just comes out 9 meters cubed. And
Oh, okay.
we could have quickly checked it. What's the volume of a pyramid in general? It is 1/3 the area of the base times the height. So 9 times 3 is 27 times a third, 9. Okay. So we did it right. Good?
Yep.
All right, so from here on out, just going to do a ton of examples.
Sweet. Yep, good. Sounds good.
Let's do another example. Do you guys have your book?
Yeah.
Because this next one has a picture that there's no chance I'm going to be able to draw.
What example?
Example 2 on page 310. But I'll try and scratch out the idea, and then I'm going to have to draw awful. So what we've got is we've got some cone. Is it centered on the XY?
Yeah.
Yes.
That's the word.
So the center here, this is our x-axis. Just awful. Try this a little bit better. That should be our center. Let's make that dotted. Try and make it very clear. All right, so here is the center. My y-axis, I'll draw this way. So my y-axis starts at this point and it's coming out this way. There's my y. And my x-axis is running this way. And then my z-axis comes up through that point out the top. I don't know. Is it still clear to you guys what I have drawn here?
You said this was example good.
Example 2.
Why is that a weird shape?
Does not look like a weird shape.
Doesn't look like a weird shape yet, right?
You mean example 2 or example 3?
I don't know.
Because this is example 4.
Yeah,
Oh, okay.
that's example 2. That is what we're going to be talking about. Now, I've got start out with this cylinder, and it's sitting on the XY plane. You with me?
Yep.
Yep.
Now I am going to cut a 45-degree angle that goes through the y-axis. So I'm cutting off a wedge out of that cone.
Okay.
And so it creates an orange-looking wedge, like a orange slice wedge-looking thing.
Yeah.
So I come and I slice right here, right through it, and it comes over here on that part, and it cuts out this wedge right here. I'm now going to draw what that wedge looks like right from the side that we cut out. Looking at it perfectly from the side, the wedge looks like this.
Yeah.
Looking at it from a bird's eye view, the wedge looks like a half circle. We cut down right through the middle of the cone, or right, start from the middle of the cylinder, went out at 45 degrees and cut.
Yeah.
And cut off a wedge looking thing. We're in trouble, because I can't draw worth anything. That's why I'm saying look at the picture that you have on your figure. It shows the wedge that we're talking about, and that will help you see it. Now, this cylinder had a radius of 3.
Okay.
You with me?
Yeah.
Okay, so here is our x direction. Let me draw, for our sideways look, this is the x direction, this is the z direction, right?
Yeah.
Okay.
And if we're looking down with a bird's eye view here, looking down on it with a bird's eye view, does it go through the x-axis or the y-axis? It goes through the y-axis. Okay, I drew it correctly. And looking at it this way, so here is looking at it from a bird's eye view. So here's the y-axis, here's the x-axis, and from here, it goes from 3 down to -3, and it just looks like a semicircle.
For your second picture, shouldn't that be X and Z, not 2, 1?
Something. Looks awful. Making a mess, trying to make it clean. Goes out 3 again. For my second one, this should be X and Y. That's looking down on it from the Z direction.
Your side.
This side one is X and Z. It's if I take that wedge and I
Oh.
stick it so that y is coming right out the board into my eyes.
Okay. Yeah, okay.
You see it?
Yeah, I just misread that.
Okay, so now we're going to take a bunch of slices of this wedge. So what is our volume? Our volume is going to be this infinite sum of little dv's. If I take a slice of my wedge right here, so I take that slice from a bird's eye view, that's this slice right here. So this slice and this slice, the same thing. This is looking out sideways, this is looking out from above.
Okay.
And my slice is a little rectangle.
Yeah.
You with me? Okay, so now question, what is the height of my rectangle here?
Let's see.
Yeah, it's the z coordinate.
Yeah.
But this line right here is z equals x. It's just a line with a 45-degree slope.
So it's just gonna be.
So it's also just x, but we'll keep thinking about it as z for now. So z is our height here. Now we need our width here.
Which is 6.
What? No, because it changes as we go, right?
Yeah.
So what is my distance from here to here?
It's just going to be.
It's just the y coordinate.
Right.
And then my distance from, now my distance from here to here is going to be
2, 1.
double my y coordinate,
Oh yeah.
right? So z times 2y times, now, which way are we taking our slices? Are we taking them in the x direction, the y direction, or the z direction?
How does it give you the same result for all?
The extra.
X direction, I think.
With the way we set up, we're taking, this slice was in the x direction. What is the thickness of this slice? Or the thickness of this slice?
I know.
It's an arbitrarily small change in the x direction.
Don't you need to take both integrals for that to get the?
No, this and this are the same picture. It's just looking at two different ways because I can't draw a three-dimensional one.
It's technically a full square.
It's a rectangle.
You have your length and then you have your height.
So this rectangle, its height is z, and its length is 2y. And now its thickness is an arbitrarily small change in the x direction, dx.
Yeah.
That's how we took our slices.
Yeah.
See it?
Yes.
So now, since our slices are in the x direction, we need to write z in terms of x, and we need to write y in terms of x.
Oh,
And then we can integrate it.
Yeah, that's fine.
So this equation was z equals x. So I can rewrite this as v is equal to, oh, and what were the bounds on our integral? Our x starts at 0 and goes to 3. Good?
Yeah,
Okay. So 0 to 3, z is the same thing as x, times 2 times, now our y. What is the equation for this circle right here?
For the semicircle?
Since it's, well, think about it for a whole circle. What's the equation of the whole circle?
Y squared plus x squared equals y squared.
It's x squared plus y squared equals 3 squared.
Or not.
Because it's a circle of radius 3 centered
That's 0.
at, at the origin,
Yeah.
right? So what is y then? Y is equal to the square root of 9 minus x squared. Subtract x squared from both sides and then take your square root. That gets you your y.
Yeah. Yep.
Okay, so 2 times y, which is 9 minus x squared, and then we have a dx. All right, now this is something like what would have shown up on your last test. How do we solve that integral?
U substitution.
U substitution for the 9 minus x squared. So I'm going to say let u equal 9 minus x squared. And so what does du equal? What's the derivative of this thing?
Negative 2x.
Negative 2x, chain rule, dx.
Yeah.
Or in other words, remember how we got that. Du dx is equal to negative 2x, multiply both sides by dx, and we get that.
Yeah.
Okay, so rewriting this out, our volume is equal to the integral from 0 to 3. Well, should we change our bounds?
Yeah, 2.
Since we're doing it as u, we also need to change our bounds. So it's no longer as x goes from 0 to 3 because our new variable is going to be u. Let's plug that in last. Let's see. So negative 2x dx is now du. We have a 2x dx. We need a negative sign.
Yeah.
So I put a negative sign here and bring a negative sign outside. Two negative signs is positive. We're back to where we started. So this negative x2 dx all together is my du. And now we have the square root of u, or in other words, u to the 1/2.
Yeah.
Good? And now what are our new bounds? So it used to be as x went from 0 to 3, when x is 0, what's u? 9.
And
When x is 3, what's u?
then
0. So now we're doing the integral from 9 to 0, negative, don't forget our negative sign. That negative sign.
Yeah.
This negative 1 went into getting our conversion from dx to du. That negative sign is still there. Okay, so now it's that integral. That's equal to, if I want to swap my numbers here, what do?
Change the sign.
Make it negative. Or in other words, in this case, make it positive.
Yeah.
And so this is the same thing as v is equal to the integral from 0 to 9 of u to the 1/2 du. Okay, so what is that?
Oh, 2/3 u.
So our volume is equal to, plus 1 gets us 3/2.
Yeah.
Divide by 3/2 is 2/3. So 2/3 u to the 3/2 evaluated from 0 to 9. Plug in 9. What's the square root of 9?
Do you switch that back? Do you switch the u back to 9 minus x squared first, or?
If we didn't change our bounds, we would have to do that. And then plug in from 0 to 3. So you can plug back in your x if you want to keep your bounds from 0 to 3. Or if you change your bounds, then you don't have to plug back in your x. It's the same amount of work either way.
Yeah.
Okay, so plugging in 9. What's the square root of 9?
81.
Square root.
Square root of 9
3.
is 3. 3 cubed is 27. Divided by 3 is,
9.
times 2 is 18. And so it should be 18, whatever our units were, meters cubed or whatever it is. 18.
That solves the whole thing.
That solves the whole thing. That wedge, had an area or had a volume of 18 units, whatever our units were.
So why did you pull out the wedge?
What?
Why did you pull out the slice?
Because that was.
Oh no, we found the volume of the slice. I just drew this cylinder to help you understand what that slicing was, what we were
Oh,
slicing.
so that wasn't-
That's why I said, look at your picture.
Yeah.
I thought it was-
So no, we did not find the volume of this cylinder. We found the volume of that wedge that we cut out.
Yeah, I got you.
Okay, next. The region between the curve y equals the square root of x from 0 to 4 and the x-axis is revolved around the x-axis to generate some volume. Okay. If I can do this half decent. So we are taking the function. This is the function y is equal to the square root of x. And we went only up to the point x equals 4. So that gives me this region right there. I am now going to take that region and I'm going to revolve it around the x-axis. I'm going to spin it around here.
Why?
So it's going to come out and go back into the whiteboard somewhere down here. Right? Spins, goes back in there, and it creates some sort of bullet-looking shape.
Yeah.
You with me? Our job is to find the volume of this bullet-looking shape.
So why did you flip it down? Is that part of the problem?
That's part of the problem. The problem says, look at this region, bound between y equals the square root of x and x equals 4.
Okay.
Here's that region. They say find the volume you get when you rotate that region around the x-axis. Okay? So when I take some little slice of this thing, so when we do that, it's going to create some volume. Maybe draw roughly what this picture will look like to the side, although probably in trouble again.
Circle.
It's going to look something like that when we spin it out.
What side is that?
Here's the tip. Over here, that point's right there. Take this and spin it, rotate it around this axis.
Okay.
And it's going to create a shape that looks something like that.
Okay.
Am I losing you?
You're spinning it that the way the arrow shows?
I'm spinning it around the x-axis.
Oh.
So it's like I cut that out of the blackboard, cut out that shape,
Yeah.
and I put a rod right here through the bottom of it, and then I spin that rod.
Yeah.
And so it's going to fold out and then roll back up in and go out again. And it's going to create a shape that looks something like this.
Like a weird cone. Or a white cone.
Yeah. Okay, I got.
Okay, so what is a little slice of that new shape going to look like? I take that slice, that's the same as this slice right here, and yes, you already see it. It's going to be a circle.
Okay.
So how do I get the volume here? The volume is going to be the integral from, which way am I taking my slices? This was y, this was x.
X, Z.
I'm taking my slices in the x direction.
Or, oh yeah.
So it's ultimately going to be a dx over here.
Okay.
I'm going from 0 to 4 in the x direction. And now, what is my area? What is my cross-sectional area? It was a circle. What's the area of a circle? Pi r squared.
Sorry, pi r squared.
So what do you take?
So, our volume is pi r, we got to get the radius, we want it as a function of x, squared, and then dx.
Why is the X there?
Since we have a dx here, we want to express this as some sort of function in terms of x.
Yeah. Okay. Alright.
Let's forget that for a second. I'll write that way the next time. But for now, let's just keep it like this. That's going to be our volume, right?
Okay.
What is the radius of the circle?
Square root
It's
of
whatever.
It's just this height. It's just y.
Yeah.
You with me?
Yeah.
So this is y squared.
Oh yeah. Okay.
Because y is the radius.
Yeah. That makes sense.
Okay, but now, since we have a dx here, we want to express y in terms of x.
Yeah.
That's why I did r of x, meaning the radius, but in terms of some x. That's all that meant. Okay, so now this is equal to, what is y squared in terms of x?
Root X squared. So just X.
Just x. So this is just the integral from 0 to 4 of pi x dx.
Yep.
What's the integral of x? Integral.
X squared over 2.
X squared over 2. So this is going to be pi times x squared over 2, evaluated from 0 to 4.
Don't you need to change the 0 to 4?
No, we didn't do any u substitution or anything.
Oh.
Those were our initial bounds. Our slices started at 0 and ended at 4.
Okay.
Your bounds are just the direction you're slicing in, where you start taking them and where you end.
Yeah.
Okay.
Okay. Plug in 4, what do you get?
4, 16, 8.
8.
Oh.
So it's just 8 pi. Double check. 8 pi. Good?
What do you mean to not do example 3?
Example 3 isn't really an example. It's a, hey, notice this thing? Okay, example 5. A circle, okay, basically coming up with the equation for a sphere now. So this time we've got some top half of a circle that we're looking at. It's going to be a very similar type problem. Can you use A for the radius? Yes. Okay, so it starts A, negative a, something like that. Sorry, not great.
Okay.
So we've got the top half of a circle here, and now I'm going to rotate that around my x-axis. You know it's the x-axis. I'm going to rotate it around this axis, half a circle. So I'm going to let it come out, go in, flip around, and it's going to create a
Oh.
what shape is that going to create?
What shape?
A sphere.
A sphere,
Yeah.
like a ball.
What is that right now?
So we're talking about this thing. A semicircle is what it's supposed to be, half a circle. That's what it's supposed to be.
Okay.
So you got that semicircle, you take it and you fold it out and it goes back in. You're spinning it around this
Okay.
axis,
Which makes a circle.
Or a
which
sphere.
makes a sphere, because it comes all the way out into three-dimensional space
Yeah.
and then goes back into the board. So it does come back into the board
Oh.
down right here, but it keeps going all the way around.
Okay, I see.
You can't talk about the volume of a two-dimensional shape.
Right.
So we're talking about a volume generated by taking that area and wrapping it around.
Okay.
Again, what is our cross-section going to look like if we take a little slice of that thing? It's going to look like a circle.
Oh, yeah, that's.
I don't know who stole my globe. It's going to look like a circle there, right?
Yeah, so we got the last one.
And so our volume of the sink is going to be, we're going to take our slices this way in the x direction.
Just gonna be pi.
So it's going to be the integral from, where do we start taking our slices? Negative a. We end taking them at a.
So there's no numbers.
What? Oh, yeah. There's no numbers. The circle had a radius of a, that's all we know.
Okay.
Okay?
Yeah.
So pi.
What is the area of the sink? What's the area we get?
Pi a squared.
Pi r squared, right?
Yeah.
Which is radius.
The radius changes. It is not always a. When we're over here, this slice, the radius of that circle is small.
Yeah, but it's.
This slice radius is bigger. Here, the radius is a, and then it gets smaller again. The radius of our slices is not always a.
Oh, so
We're talking about the radius of the slices that we take of the sink.
it's just y.
It's just whatever the y is. Perfect. So this is the integral of pi r squared times dx. This method is also referred to as the disk method. We're breaking this up into a bunch of disks. Circles with a teeny bit of thickness, so they're actual disks.
Yeah.
Make sense?
Yeah.
Okay. Now what is y? This is a circle. So the equation of this thing is x squared plus y squared equals a squared.
Yep.
So what does y squared equal?
Y squared equals
Y
a squared minus x squared.
Perfect. So this is just equal to the integral from negative a to a of pi times a squared minus x squared. Good?
Yeah.
Okay, so let's take that integral. So our volume is equal to, pull the pi out. What is the integral of a squared with respect to x?
2a over 3.
No, no, no. What is the integral of 17 with respect to x?
Oh.
17.
Oh.
0.
Oh, 17x.
Just 17x.
Oh.
Look, 17 is the same thing as 17 times x to the 0, if that helps.
Yeah. I got it.
Okay, a is just a constant.
It's just
A squared is just a constant. What's the integral of a squared?
A squared x.
It's just a squared times x.
Okay.
A is just a constant,
Yeah.
just like 17. So this is a squared x minus, what's the integral of that one?
oh, but this is the one where it's 3.
X cubed over 3.
Okay, I see.
Yeah, because that's the actual variable
That's the actual one.
that we're integrating with respect to.
That makes sense.
So we're doing this, and we're going from negative a to a. You with me?
Yeah.
Now, maybe you can notice this function is even, and going from negative a to a is the same thing as going from 0 to a and just multiplying it by 2. could have done that clear up here. We could have said 0 to A and just put a 2 out in front.
Yeah.
In other words, just doing half of it and then double your result.
Yeah.
And that way you only have one number that you actually have to plug in, keeps it a bit simpler. But you could have done negative A to A without the 2 there and been fine. Wouldn't have changed anything.
Yep.
Okay. Now, let's plug that in. What's A squared times A? A cubed minus A cubed over 3. So I got A cubed minus a third of A cubed. I'm left with
2/3 of A cubed.
2/3 of A cubed. So I've got 2 pi times 2/3 of A cubed.
Yeah.
2 times 2 is
4.
4. Woohoo. So this is equal to 4/3 pi times our radius cubed. The equation of a sphere, the volume of a sphere. 4/3 pi, your radius cubed. All right, so there's that formula. Next, find the volume of a solid generated by revolving the region bound by y equals the square root of x, y equals 1, and y equals 4. That must have been x equals 4. And I read it wrong.
What is the example you want?
Example 6. All right, so we've got x equals 4 is this line. Y equals 1 is this line. And then the square root of x comes up due, I'm not going to bother drawing that part, but from here it goes like this. And we're looking at this region. So square root of x equals 4, y equals 1. With me?
Yeah.
So that's our region. I'll erase that line, we don't really need it. We just need to know that this region is bound by 1 and 4. Now this time, we are rotating it about the line y equals 1. So this is the line y equals 1. That's the line that we are spinning this around. So it's going to come out and go back through the whiteboard down something like right there.
Yeah.
Okay? So we're going to break this up into this again. Break it up in the x direction. What is one of our slices going to look like? A circle, once again. And so our volume is going to be equal to the integral from, where are we going to start taking our slices? 1 to 4. What's our radius?
It's y.
Or no, it's y. Right?
Y is the distance from here to here.
Oh, it's
1
gonna be
minus 1 is
y. Yeah.
It's going to be y minus 1. That's this distance. Here's our radius.
Yeah.
Oh, okay.
The end point minus the start point gives you the distance. So that is our radius. Our radius is y minus 1. So the equation of this line right here was, I didn't write it, it's y equals the square root of x, right? So our radius is y minus 1. It is y minus 1 squared, because it's your radius squared, pi r squared.
Okay.
And then we were taking our slices in the x direction, so dx. With me?
Yeah.
So this is equal to, let's pull our pi out, and then square this thing away. Square root of x times square root of x is x. Square root of x times negative 1,
Negative.
negative square root of x. Negative 1 times square root of x, another negative square root of x, so we have minus 2 square root of x. And negative 1 times negative 1 is 1. And now, dx. So just multiply that out and pull the pi out in front.
Yeah. Yeah.
Okay, now it's integrated. So our volume is equal to what? We still have the pi. What's the integral of x?
X squared over 2.
X squared over 2, not derivative. Integral. Square root of x, that's the same thing as x to the 1/2. So what's the integral of that? So we have minus 2
3 over 2. X to the 3 over 2 over 3.
x to the 3/2, right? And then multiply it by 2/3. So the 2 in the top is going to turn this into a 4.
It's going to be over 3.
Oh.
and over 3. You okay with the algebra I did there?
Yeah.
Okay, and then finally, what's the integral of 1?
1x.
X. 1x, I think. And now we need to evaluate this from 1 to 4. So plug in 4 and subtract what I get when I plug in 1. So this is going to be pi times, let's plug in 4.
16.
8. What's the square root of 4?
Square root.
Square root of 4 is 2. Cubit is 8. Times 4 is,
64.
8 times 4 is
32.
32.
That's what I said first, right?
I don't know. I heard a bunch of answers.
I think I said
I caught myself.
We'll pretend you all said it right. Okay. And then plugging in 4 for x is just plus 4.
6.
Now subtract what we get when we plug in 1. So I'm going to plug in 1, make it negative.
Yep.
So plugging in 1 here, what do I get?
You get 1/2.
1/2, make it negative. Plug in 1 here, what do I get?
Why is it making it negative?
Because I subtract what I get when I plug in 1.
Oh, gotcha.
So I'm distributing the negative through as I go.
Oh, couldn't you have combined all the answers and then just
We're about to
subtracted it?
I don't know what
Oh,
you
I
mean.
see. He means combine all of the constants before we subtract 1. Like 8 minus 32 thirds plus 4.
Ah, sure. I'm just going to simplify it all in one go. Okay. Plug in 1 here, what do we get?
4/3.
Minus 4/3, make it negative is positive 4/3.
Minus 1.
Plug in, we get 1, make it negative is minus 1. Right?
Yeah.
Now I'm going to do everything in terms of thirds and subtract 1/2 when I'm done. Okay? I don't know. There could be an easier way. That's just what looks easiest to me.
If we combine, no, never mind.
Okay, 8 in terms of thirds is,
24/3.
so we have 24 thirds minus 32 thirds plus 12 thirds, skip that for a second, plus 4 thirds minus 3 thirds, and then finally minus 1/2 when I'm done. With me?
Yeah.
So we're going to have the pi here. 24 minus 32 is
-8.
plus 12,
Positive 4.
positive 4 plus 4,
Positive 8.
minus 3,
Positive 5.
5. So we get this 5 thirds minus 1/2. And now we'll convert to 6. So I get 10/6 minus 3/6 is
7/6.
7/6. So this should be 7, 6, 5. See that? Make sure that's all okay. 7 by 6, yeah. All right, move to the next part. Guess it's kind of 6s. I have to erase something. Make sure I get one of the edges. Shouldn't go past here. Okay. This marker works. While I'm erasing this, will one of you read me the next example?
That's example 7.
I guess I'll finish erasing as we go.
Find the volume of the solid generated by revolving the region between the y-axis and the curve x is equal to 2 over y. And y is between 1 and 4 about the x-axis.
Y goes from 1 to 4.
Okay. Y-axis, sorry.
Yeah. So we got 1, 2, 3, 4. Our curve was what? Y equals 2 over x? Or x equals 2 over y? X equals 2 over y. And so right there. Let's see, when y is 4, x is 1/2. So So our shape very roughly looks like this. And we were revolving about the y-axis, right?
Yeah.
Okay, so here's the region we care about. And we're revolving it about the y-axis this time. Right? So which way do I want to take my slices?
Y, X.
I want to take my slices this way. I want to take it in the direction that we're spinning this in.
Yeah.
Because that's the direction that I get circles.
Oh, yeah.
That makes sense.
Right?
Yeah.
So one of my slices, when this comes around, it's going to go back into the whiteboard that way, right?
Yeah.
But so one of my radius slices, one of my radiuses is going to be like this thing.
So it's X this time.
And it's just the x coordinate. Perfect. So our volume is going to be the integral from, where do we start taking our slices?
1.
1. Where do we end? 4, because we're taking our slices this way now. Of pi r squared dy.
Yep.
Good?
Yep.
Now, obviously, we want to express x in terms of y. Fortunately, the author gave us the equation in terms of y. So this is equal to, pull the pi out. We have the integral from 1 to 4 of this thing squared is just going to be 4 over y squared dy. Right? Or, pull the 4 out, 4 pi times the integral of y to the negative 2, in case it helps you. Okay, from 1 to 4. So what is the integral of y to the negative 2?
It is y to the 1 over negative 1.
Right, so negative y to the 1.
Yeah.
Or in other words, so we're going to get 4 pi times negative 1 over y, or y to the negative 1, same thing,
Yeah.
and evaluate it from 1 to 4. So this is equal to 4 pi times, what do I get when I plug 4 in? Negative a fourth. Now subtract what I get when I plug in 1. So when I plug in 1, what do I get? 1, I get negative 1. Now subtract negative 1 gives me plus 1.
So 5 fourths.
Sanity check really quick. When you're doing these problems, you can't get a negative volume. So if I would have screwed up and accidentally made this minus 1, my volume would have come out negative, and that would have told me you for sure did something wrong.
Yeah, that makes sense.
Okay, anyways, 1 minus a fourth is 3/4 times 4 is just 3 pi. Good? Double check with the author, 3 pi. Okay, our next one here, we've got a parabola in the x direction, and that is the line x equals 3. Yes. So, see if I can do this somewhat decent. 1, 2, 3. Here's the line x equals 3, and then we've got our parabola here. Our parabola is a parabola, x is equal to y squared plus 1. How do I graph x equals y squared plus 1? Yeah, just think about it as a parabola tipped on its side. So you're thinking about x as a function in terms of y. If you're getting stuck on these, by the way, when you know that you have to express x in terms of y, you can always just change your picture. And I can instead say, you know what, I'm going to look at it like this.
X is 0.
And make this my x-axis and this my y-axis. And just flip your picture and think about it like this if it helps you, rather than having to think about it like this. You like this way better.
So we're not going to do it.
Now, you can do that if you would like to, as you get used to it, but eventually you just got to get to the point where you can just see it however I draw it.
Yeah.
So this is helping to prepare you for physics next year. You got to deal with whatever your physical scenario is, but if you get stuck, feel free to do it that other way. Now I didn't draw this very good. What are our bounds here? How high up do we go here?
3.
When x is 3, what is y?
What? Oh, 10?
When x is what?
When x is 3, what is y?
3, move it over. That's
Square root of 2.
Just the square root, come on. Like, 3 is equal to y squared plus 1. Subtract 1 from both sides. 2 is equal to y squared. Square root of both sides, y equals plus or minus the square root of 2.
That's it.
So the y here, it goes up to square root of 2. And it comes down to minus square root of 2. Because I know it goes over to where x is equal to 3.
Yeah.
Okay. So here's our function. It's x is equal to y squared plus 1. That's our function right here. This is x equals 3. Okay, which way are we taking our slices? I can't remember. I assume we're spinning this way.
Does it matter which way we spin?
Yes. Oh, very much which way we spin. We are not spinning that way. We are spinning about this axis. So we are spinning this way.
Oh, so
Because you're always going to want to take your radiuses in the direction you're spinning.
But
Because in the direction you're spinning is the direction that you're going to produce circles.
why do you need to spin?
it's just the way.
It's what the problem is. It says find the volume by taking this region and spinning it about this axis.
Why did you do that?
It doesn't
It's just a way of describing a shape. Imagine that shape. Take this, spin it around there. Now tell me that shape.
I can just tell you the shape.
How else would you say it? Take this parabola and spin it around there, that's the shape. Tell me that shape without describing it that way.
It's a sphere.
That's not a sphere, because this isn't a half circle, that's a parabola thing.
Yeah, you're probably right.
Parabola. Okay, so we're going to take that and we're going to spin it this way.
Yep.
So which way do we want to take our slices?
Up and down. Why?
In the y direction. Our slices are going to go this way, so the radius we care about is this radius. Right? Okay, so once again, our volume is equal to the integral from negative 2 to 2, or negative square root of 2 to square root of 2,
Yeah.
of pi r squared. Pi, what is our radius?
The radius is y.
The radius is x minus 1.
True 2.
Our radius is this thing.
Yeah.
Oh,
How do you get this thing? You take the end point minus the start point. What's the end point?
0.
3.
Where's
1, 2, 3.
Yeah. It's true.
Oh, I have you in the negative direction. I thought that was.
Okay, what is our start point? Whatever the x coordinate is,
3 minus x.
right? So this distance is end minus start, or
3 minus x.
3 minus x. If I subtract this, I need to make both of them negative. Follow the algebra?
Yeah.
3 minus x. You with me? We'll take this one step at a time. 3 minus x squared dy, because we're taking our slices this way.
Yeah.
Since it's a dy, I need to express x in terms of y.
Yep.
Okay, so this is going to be v is equal to. Now, rather than doing the integral from negative root 2 to root 2, I'm just going to go from 0 to root 2 and double it.
Okay.
Okay, that works.
Again, you can keep it negative root 2 to root 2 and it come out the same way. It's just slightly easier. So 2 integrals from 0 to root 2 of pi, should pull out the pi as well, so 2 pi out front. And we get 3 minus x dy. Good? Okay, so this is equal to 2 pi times the integral from 0 to root 2 of 3 minus 1 is 2, so 2 minus y squared dy. Okay, so what is that going to be? Integral of 2, 2y. Integral of y squared,
Y cubed over 3.
y cubed over 3. And now we evaluate that from 0 to the square root of 2. What do we get when we plug in the square root of 2?
One is 2, but I'm wrong.
We get 2 square roots of 2
Which is 2 root 2,
minus,
root 2 cubed. So,
what's the square root of 2 cubed?
3. It's
What's the square root of 2 times the square root of 2 times the square root of 2?
It's 2 to
power of 3 halves.
3.
2
It's 2 root 2.
2 root
2 square roots of 2.
Yeah.
It is also 2 to the 3 halves, but 2 square roots of 2. So we have
Yeah.
2 square roots of 2
Over 3.
2. Oh, why did we do that?
minus 2 square roots of 2 over 3.
Oh, really?
Okay.
Interesting.
Okay. Maybe think about pulling the square root of 2 out. And what's 2 minus 2 thirds?
2 minus 2 thirds.
What's 6 thirds minus 2 thirds?
Or 4 thirds.
4 thirds. And then we have that was pulling the square root of 2 out. So we have 2 pi times the square root of 2. And then we did 2 minus 2 thirds is 4 thirds. And finally we get 8 thirds pi square root of 2. With me?
What happened to the root 2?
It's right. It's still there.
There's 2 root 2s. What happened to
You took them out by,
Whoa. I got way off.
what was,
What? The answer was 64 pi root 2 or 15. How did we get 8 through pi?
Pi r squared. Pi r squared. I can't believe I missed that. All right. Let's try this again. So integrating that, what do we get? We get 2 pi times,
We need to do like a resubstitution.
oh, let's do our integral really quick. Integral from 0 to the square root of 2.
Why?
Oh, we could have still left it how we had it before. 3 minus 1 is the same thing as just 2.
Yeah.
So this is the same thing as just 2 minus y squared. You okay with that?
Yeah.
Okay, now let's just multiply that out. So 2 times 2 is 4. 2 times negative y squared is negative 2y squared. Then we get the other one for a total of negative 4y squared. And then negative y squared times negative y squared is plus y to the 4
all that squared?
dy. I'm just squaring this out. So I have this times itself. I have this times this and this times this. Both those are there. And then I have this times itself.
Okay.
Yeah.
Okay, now integrate it. What do we get?
4y.
Minus
This
4
thirds
cubed.
y cubed.
4 thirds pi cubed. Plus y 5 over 5.
Okay,
Evaluated from 0 to
let's see if we've got the same thing as the author so far. 4y minus 4 thirds y cubed plus y to the 5 over 5.
Yeah.
Okay, and you plug it in and it comes out 64 pi squared to 2 over 15.
Plug in 1.
and the algebra.
Root 2.
When you evaluate this from 0 to square root of 2.
Oh, we're just gonna skip it.
Yeah, we're gonna skip it. I'm not gonna plug all that in. But you could just plug it in on your calculator really quick. Okay. Next one, example 9. Now we're introducing the washer method. So far, when we've been doing these rotations, we've been using what's called the disc method, because you can think about what we've been cutting this into was a bunch of little discs. Next, we're going to be breaking them into a bunch of little washers with an arbitrarily small thickness. Washer like,
The circle with the broken
Yeah.
circle.
yes.
So
So where your cross section looks like this thing.
An area of the circle minus the area of the circle.
Area of a bigger circle minus the area of the smaller circle. And it's going to be for when you spin it around something that's not exactly next to it. So let's do an example. Example 9, y equals x squared plus 1. So we're looking at y equals x squared plus 1, and we're also looking at y minus x plus 3. Y is equal to negative x plus 3, so let's get a sense for this thing. I'm gonna need a height of 5. Should have thought about this ahead of time. Okay. So 1, 2, 3, 5, 1, 2, 3. Okay, so y equals negative x plus 3. That has a y-intercept at 3 and then a slope of negative 1. Right? Something like that. If I can get these half decent. Okay, there's one of our lines. And then our other one is just the parabola. Y equals x squared plus 1. It's going to come down like this. And then let's see, 2, 5 is where it's going to intersect. Something like that. So we're starting here over at negative 2. I didn't drop too good. And going over to 1. You with me?
Yeah.
Now, we are rotating about this axis.
Yeah. Okay.
So that's what the problem asks us to do. Now, we're kind of in trouble because, so we're going to take one of our slices this way. When I spin this thing and it goes back in the board, drawing out where it goes back in the board extremely roughly, don't read too much into this, it's going to look something like that is where it would slice back into the board, right?
Yeah.
I pull this out, we're rotating about this axis. So it's going to come out and then spin back in right there. And so if I take a slice of this thing, a slice right here, has a hole, and then comes right there again, it's going to look like a washer. Where this piece is where we miss, and this piece are right there. Right here and right here. Right? This is going to be a weird ring-looking thing that has a hole through the middle that you can see through, right?
Yeah.
Why were the other ones that way?
Because we were always touching where we were spinning around. The figure actually touched where it spinned, and so there wasn't any hole in the middle.
So where is it asking us to spin?
So this one, it's asking us to spin around here,
Right there.
around this axis. So it's going to come instantly out of the board and then go back in right there. So it's not touching where it spins.
Oh.
This one, where it went back into the board, was right here.
Yeah.
And so it's touching the entire way through. And so a slice of this looked like a little disc. A slice of this is going to look like a washer. If I pulled out that slice and looked at it, it'd be a washer. That make sense?
Yeah.
And so what is the area of a washer?
It's the big circle minus the small circle.
If we call this radius big R, and we call this radius little r, what's the area?
Big R minus R.
Pi of r squared minus little r squared, right?
Yeah.
You good with that?
Yeah.
Okay, so that's exactly what we're going to be doing here. So our volume of the sink is going to be the integral from, where do we start taking our slices? -2 is where we start, and we're going this way.
Oh,
-2 to 1 of pi times our big radius. What's our radius from here all the way up to there?
it's
Yeah, but it's this way. It's y equals negative x plus 3.
So negative x.
Oh.
So negative x plus 3. Let me put square brackets here just to help us see exactly how we're plugging this in. So there's our big R squared
And then minus.
minus our small radius. Our small radius is the distance from here to here, the portion we're removing.
Okay.
It's
It's just the y of this function.
Which
It's
is
just the y of this function minus the y of this function.
okay. So what would that be?
This bottom function is right here. It's just minus x squared plus 1 squared.
Yeah.
Okay.
Look, let's do this one more time. Let's call this function, the top one, I'll call that y1 equals this thing. And this function right here, the bottom one, is y2 equals x squared plus 1. You with me? So then our radius to the top here, so it's pi times our distance from here to this one is y1 squared minus our distance from here to here is just y2 squared. From here to here is just the height of this function. From here to here is just the height of this function. Okay, so that times, what is one of our little slices?
It's y.
What's the thickness of our slice?
dx.
Dx. So we got to write things in terms of x.
Okay.
So our volume is equal to, pull the pi out. We got the integral from -2 to 1. I'll do square brackets for these brackets. y1 squared, y1 is this. I'm going to write that as 3 minus x rather than negative x plus 3. Oops, minus. Good with that? Okay, so now, let's square it all out. So the volume is equal to pi times the integral from -2 to 1 of 3 times 3 is 9 minus 6x plus x squared. That's multiplying out this, right?
Yeah.
X squared times x squared is
X
x to the 4, make it negative. X squared times 1 is
X squared.
x squared, and 1 times x squared is another x squared, so 2x squared, make it negative. And then 1 times 1 is 1, make it negative.
Is that 2x squared? Right? From the center one?
Yeah.
Yeah.
This one, thank you. Did I do it all correctly? Okay, and now that is equal to pi times the integral from -2 to 1 of, let's see, 9 minus 1 is 8. How many x squareds do we have? 1 minus 2 is minus x squared.
Wait.
We have 1 here and -2 there for a total of -1 of them.
Yeah.
And x to the 4, we only have 1, right? Okay. And now that is equal to pi times 8x minus x cubed over 3 minus x to the 5 over 5. evaluated from -2 to 1. Is that correct?
Yep.
All right, this is equal to pi times, plugging in 1, I get 8 minus 1/3 minus 1/5. Now plug in -2, I get minus 16.
Well, that's plus, right?
Make it negative. I get, because I'm subtracting what I get when I plug that in.
Yeah, you get,
Plug in -2 here.
yeah.
I get positive 8/3. Make it negative. Plug in -2 here. I get positive 32/5. Make it negative.
Isn't that 5? Where do you get 32?
What's 2 to the power 5?
25.
2 to the power of 5.
What's 2 times 2 times 2 times 2 times 2?
32.
Oh, it's 2 to
2 to the 5, not 5 to the 2. Right?
Yeah.
Is there a clever way to do this?
It's 15.
Use 15. Why do I get the feeling like we did something wrong? We were doing this one. 8 minus, oh, I lost our 6x.
Oh,
Son of a gun.
Right.
Minus 6x minus x squared minus x to the 4. Right?
yeah.
Wait, where'd you get?
There's 2.
Oh, right. Okay. I see.
Okay. Now this is equal to pi times 8x minus 6x squared over 2, or 3x squared, minus x cubed over 3 minus x to the 5 over 5, evaluated from -2 to 1. Okay, let's do this again. We're going to get 8 minus 3 minus 1/3 minus 1/5
Minus.
plus 16.
Plus.
Negative 16, make it negative is positive.
Negative 12.
Negative 12 becomes plus 12, right? This one is negative 8/3. And this one is negative 32 over 5.
Why wouldn't 8/3 be positive?
Plug in -2 makes it positive, and now we're subtracting what we get when we plug that in. Let me really quick make sure we're on the same track as him. 8x minus 3x squared minus x cubed over 3 minus x to 5 over 5, evaluated from -2 to 1. Okay, let's see. You see anything simple to do with that?
Combine your constants.
Yeah, I'm thinking about a way of adding them up.
15.
I can just do it in my calculator across.
Yeah, we won't bother with that. So, plug it into your calculator, and you get 117 pi over 5, not over 15.
Must simplify.
Well, they reduced it.
Yep, let's simplify. But it comes out 117 pi over 5. And we'll take the author's answer. We'll assume he didn't mess up.
It's because you get 3/15 when you take the 7/3 and move, you get 35 15s, or 35. Yeah, trust.
All right, we'll trust. Okay, so we've calculated volumes just by adding up cross-sectional areas. We've done it where we were rotating and we use discs. We've done it where we've been rotating and we use washers. Now there's one more method out there, and it's called the cylindrical shells method. So we'll do a couple examples with cylindrical shells, and then we're done.
Done for the next section.
For both sections.
Oh, we've already moved over. What did we move over?
We're moving right now.
6.2 is the.
6.2 is just cylindrical shells, and it's a small section.
Oh.
Okay, so we're looking at the region. Let me look. I'm going to do example 2 first and then go back to example 1. I think it's a slightly easier one to get to start with. So example 2, we're using y equals the square root of x and x equals 4.
Example 2 uses the shell method.
So going over here to 4, here's our region. Let's see, the region bound by y equals the square root of x, the line x equals 4 is revolved about the y-axis. So we're revolving it this way.
From which line?
So revolving it this way, this region.
Is that not meant to be slanted?
Those are.
This is y equals the square root of x, is the top function.
I know, but you're
They are.
right. They're meant to be slanted.
I'm just shading in the region. I'm not taking my slices that way, sorry. We're just taking that region and rotating it.
Yeah.
You with me? So it's going to come back in the board somewhere over like right here. When we spin it around. With me? Now we could solve this using our washer method and taking our slices this way. Nothing wrong with that. Our big radius would be out to here, our small radius would be there, and we could take our slices this way.
What changes in the radiuses?
Well, I'm saying I could solve this as making it the integral from 0 to 4 of pi times our big radius, which is 4 squared, minus our small radius, which is the square root of x squared, oh, then we need a dy here.
Okay.
And it would just be x. And we would solve that in terms of y. I could solve it that way. Nothing wrong with that. This time we're going to introduce a notion, so that would be slicing it with washers this way. And one of my cross sections would look like a washer. Instead, what I'm going to use is what are called cylindrical shells. A cylindrical shell is, it's like, so looking at this thing from a bird's eye view, well, it has a hole in there. I can't really draw it from a bird's eye view.
You could.
If I drew it from a bird's eye view, it would just look like a circle. It's just a circle that slopes down inwards as you go,
Yeah.
down to a point right there, right? Okay, so looking at this thing from a bird's eye view, here's the green half, if that helps at all, and here's the half over here. Instead of slicing washers in there, what I'm going to do from a bird's eye view, imagine I have like a cookie cutter that's just like a perfect circle. And I'm going to cut into it.
Okay.
And it's going to cut out like a little cylinder just exactly where I slice. Since my cookie cutter has like a little bit of thickness to it, I would slice out just a little bit of dough, right?
Yeah.
And that dough I would slice out would be like a little circle ring with some height. it would be infinitesimally thin, right? My cookie cutter is really thin.
Yeah.
So that's going to be my infinitesimal thinness, and I would slice out from a bird's eye view just a perfect circle right here.
I know.
So right here, looking at it this way, I sliced right here, and my slice swings around, and it cuts right here.
Yeah.
So I'm slicing out that cylinder.
Okay.
You see how it's a cylinder that I'm slicing out?
Yeah.
So what I'm going to do is I'm going to take these cylinders and add all my cylinders up.
Okay.
So each one of those cylinders, imagine I take the cylinder now. I don't know how much of it I want to draw in. Because this would have its bottom part would swing around like that, and then it would come back around to the front.
Yeah. I see.
So that shell, if I were to draw that cylindrical shell over here, this is like what I cut out, right?
Yeah.
And it has just a teeny bit of thickness to it.
Yeah.
Okay, so let's calculate the volume of this cylindrical shell.
Isn't it hollow?
It's hollow, so it's just a very thin shell, so I don't know how to make it look hollow. It is hollow. Yeah, there's no clue how to make that look hollow. Alright, hollow, all we have are the sides here. Maybe you can see like that over there, and we have the sides here. Something like that. Does that help? I don't know. Maybe I'm making it worse.
That makes sense.
Let's find the volume of that cylindrical shell. Okay?
Isn't it
Is there a
just
formula for that?
Well, let's think about it. What is the surface area of that cylindrical shell?
it's a rectangle?
Imagine I unrolled it.
It's a 2.
Then yeah, it would look like this really long rectangle. If I cut that with scissors and unrolled it.
It would be a sphere.
Diameter.
No, I cut that with scissors and unroll it. Right now it's a cylindrical shell.
You cut it with
It's a cylindrical shell, meaning it's like this,
Yeah.
with some arbitrarily small thickness. I can cut it and unroll it. This is it unrolled.
Oh, okay.
Okay, so I didn't really draw the height very good. Try and get roughly the same height. So here it is unrolled. Roll it out. With me?
Yeah. Which is length times width.
So yeah, the area of this thing is its height, whatever the height is, times what is this? The length, but it's the circumference of whatever that was.
It's pi.
It's 2 pi r if this thing had a radius of r. It's the circumference.
Isn't pi how many times you wrap around?
And R is what?
Pi is the ratio of a circle's diameter to its circumference.
So why there's a 2 there?
Pi is equal to circumference over diameter. So pi is equal to circumference. Diameter is twice as big as radius. So circumference is equal to pi times 2r. So our circumference is 2 pi r.
Okay. I see.
And the height is whatever the height is. So that gives us the area of that thing. But now this thing has a very teeny thickness. And we want to get the volume. And how thick is that thing? How thick is that?
Yeah.
Dx. In this case, it's dx. Right, so let's write this out. So the volume of this thing is going to be equal to the integral. We start taking our shells at 0, and we're going to go till 4. Cutting out a shell here, 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 where our shells keep wrapping around all the way through. Each shell is going to be 2 pi r times the height, and then times r dx, the way that we're slicing. Good?
Okay.
Now, what is the radius from here to here?
It's 2.
Well, it's 2 how I drew it, but for any shell. for our cake shell, what's its radius?
S.
It's just x.
Oh, yeah.
Okay, so this is equal to the integral from 0 to 4 of 2 pi x. What's the height?
What is that for? Well,
Just y. Dx. Now, since we have a dx, we need to rewrite our y in terms of x. What is our y in terms of x?
Root x.
Square root of x. What's the square root of x times x?
X.
X to 3 halves.
X to the 3 halves. X to the 1 times x to the 1 half is x to the 3 halves dx. Integrate that, what do we get? Pulled out the 2 pi. So when I integrate x to 3 halves, what do I get?
You get
It's 2/5 x to the 5 halves.
Yeah.
2/5 times x to the 5 halves. And now we need to evaluate that from 0 to 4. So plug in 4, what's the square root of 4? 2. 2 to the 5 is?
32.
Times 2 is?
64.
Let's get that other 2.
128.
So 128 pi over 5. Right?
Yeah, for the other row.
Okay, cool. All right, so that was example 2. Now let's go do example 1. Example 1, we have y is equal to 3x minus x squared. Take a little bit of space here. So y is equal to 3x minus x squared, and we also have x equals -1. And we are rotating about the line x equals -1. Okay, so let's draw our picture here. One, 2, 3. Let's see. When is this 0? It's 0 when x is 0, and it's 0 when x is 3. It's going to reach its highest point at 3 halves. 3 times 3 halves is 9 halves, minus 9 fourths is 9 fourths. So it goes up 9 fourths. Doesn't really matter how high it goes up. Just trying to get somewhat accurate picture. Okay. So here's the region, and we're rotating around the line x is equal to -1.
Yep.
So I'm revolving this around that. So I'm going to take my cylindrical shells, and I'm going to cut each cylindrical shell here.
By
So my shell, I'm going to cut it right here,
dx.
and that shell goes all the way around, so it comes back out through the whiteboard somewhere over like right there. And it's wrapping all the way in and out. Okay. So let's calculate our volume. Our volume then is going to be the integral. I'm going to start the cuts at 0 and start cutting until I get to 4, or 3, right?
You're gonna start.
I'm going to cut.
Infinite amount of time.
An infinite number of times between 0 and 3. Okay, and I'm doing these shells. So what is the volume of one of these little cylindrical shells? It's 2 pi r, circumference, times the height, times the thickness,
dx.
Y.
which in this case is dx.
Well,
So-
minus y, isn't it?
2 pi, what's our radius?
Dx.
It's x.
X. No.
Radius.
The radius is all the way from here.
Oh,
This is what we're spinning around.
right.
So when I'm looking at this cylindrical shell, it goes all the way around to there.
Is that x equals?
Oh, I didn't.
So this is my radius.
Yeah.
So x minus 1.
Almost. Here's x. What's this? Is it bigger or smaller than x?
Bigger.
Is what? What?
So here's some point, xy, right?
Okay.
So x is the distance from here to here.
Yeah.
What's the distance from here to here?
2x.
x plus 1.
So where did I get minus from?
Because the equation of the slide is x minus 1.
Oh.
But you do the endpoint minus the start point.
Right.
So x minus negative 1 is x plus 1. So our radius is x plus 1. And then our height is
Y.
just the y. Oh, sorry, what was this equation? Oh, we have it right here.
Yeah.
So it was y, this y.
3x, x squared.
So 2 pi r h
Dx.
dx. Right? So let's pull our 2 pi out. So the volume is going to equal 2 pi times the integral from 0 to 3. X times 3x is 3x squared. X times negative x squared is negative x cubed plus 3x minus x squared. Did I do that right? Combine those two together. 3x squared minus x squared is, oh wait, these two together. 3x squared minus x squared is 2x squared. So this is going to be v 2 pi times the integral. Let's write our x cubed term first. Negative x cubed, our x squareds we have plus 2x squared plus 3x. Did I do everything correct? We're going from 0 to 3. Does that all look good?
Yeah.
Yeah.
But it looks good.
Yeah.
Going from here to here, just combining like terms. Now, I just combine this with this, and then change the order.
Yeah.
Okay, so then this is equal to, let's integrate.
Oh, you're
Negative x
okay.
4 over.
Negative x to the 4 over 4.
Plus cubed. 2 plus, wouldn't it be 4?
What?
Plus 1 to the exponent, divide.
And then that's x to the 2.
3x squared over 2.
Over 2. Okay.
And now we need to evaluate this from 0 to 3. All right, so we're going to get 2 pi times, what's 3 to the 4?
3 times 3 is 9, times 3 is 27,
81.
times 3 is 7.
81. 9 times 9, 3 squared times 3 squared. Okay, 81 over 4 plus, what's 3 cubed? 27 times 2 over 3 plus 3 times 3 times 3
27.
over 2. Right?
Yep, that looks accurate.
4 over 3.
Let's really quick write this in terms of force and combine it with that, and then I'll combine with this. So 27 halves is the same as how many force? 54 force.
54 over 3 simplifies to 18.
Okay, let me finish this. And 54 over 3 is the same thing as 9 times 6, so yeah. 18 times 3 is 54,
Which is 72 force.
which is 72 force. Cool. And this was 54 force. Okay, so negative 81 plus 72 is?
Negative 9.
Negative 9 plus 54 is?
45.
45 over 4. Oh, 45 times 2 is going to give us 90.
90.
90 pi over 4, or 45 pi halves. Is that what you got? 45 pi halves, yes. All right, last example, and then we're done. X equals y squared. Let's see. Where would be the easiest? Probably not need too much space. goes to 4.
Are we just forgetting about the z-axis?
Yeah, I'm always drawing it so that we have the z-axis coming perfectly out of the board.
Makes it easier to visualize.
So I'm keeping everything very flat.
Okay.
But there is a z-axis, right?
So what's
All these shapes, they are coming out of the board and back into the board.
So what's the distance for all that? Is that just a radius?
Yeah, all our calculations have been taking that into account. Because however much my shell goes in this direction, it also goes in this direction. And it also goes into the board. That was the radius.
Doesn't it get more complicated than that?
No. However much it goes this way and that way and that way. Because it's a radius. Right? If I take this marker, I pivot it right here and I spin it around.
What if-
However far it went this way is exactly how much it comes out. This is exactly how much it comes in. So we've just been working with radiuses.
Okay. Right.
Anyways, so this one, I think we're doing another y equals the square root of x, curve, come to the 4, double check. The region bound by the curve y equals the square root of x, the x-axis, and the line x equals 4. X equals 4 is right there. And we're revolving it around the x-axis. So we are revolving it this way. Right? Now again, we could use, in fact, we probably already did this exact problem, taking our slices like this and using discs. But this time, we're going to take our slices this way and do cylindrical shells. So I'm going to take my slice this way, and that slice is going to come out and it's going to go back into the whiteboard like right here, creating these little cylindrical shells.
Okay.
So let's get our volume. So this is going to be the integral from our shell slicing. We're going from 0 to 2.
Where are we spinning it from?
We're spinning about this axis.
Oh,
So we're going from 0 to 2. And what is it? It's going to be 2 pi r. What's our radius?
okay. Radius is y.
Just the y. Times our height. What's the height?
It's
4 minus
2.
The height is x. Isn't it?
4 minus the square root.
4 minus x.
What's the
Y.
Here's our x coordinate. Look, this is our coordinate x comma y.
Oh, I see.
That's n.
So y was our radius, and 4 minus x is our height. So it's 2 pi r h times, which way are we taking our slices?
Y.
In the y direction, so dy.
Where did you get that for?
So this is our height.
Why isn't our height just?
Our height is the length of the green line.
Yeah, but that's arbitrary.
Here's a point x comma y
Yeah.
on our curve. What is this point? How far over is this point?
0. Four.
4. The distance from here to here is 4. What's the distance from here to here? It's our end point, 4, minus our start point, which is just our x coordinate on there. So 4 minus x is our height.
Okay.
See it?
Yeah.
Okay. Now, since we have a dy here, we need to express everything in terms of y. So if y equals the square root of x, what does x equal?
Y squared.
X equals y squared. Just square both sides.
Okay.
So I'll make our substitution here. This is the integral from 0 to 2 of 2 pi y times 4 minus y squared dy.
Yeah, that makes sense.
Okay. So then this is equal to, let's pull the 2 pi out of my integral. 2 pi integral 0 to 2. Y times 4 is 4y. Y times negative y squared is negative y cubed, dy.
Yep.
So we get 2 pi times, what's the integral of 4y?
Wouldn't that be a over 2y to the squared?
Oh, I see.
Why? That's why it's
4y squared over 2,
It's 2y squared.
or 2y squared.
Okay.
We have 4y to the 1. Add 1 to the exponent gets us to 2. Now divide by the exponent.
Yeah, I do.
All right, so we get 2y squared minus, what's this one?
Which is y 4 over 4.
Y to the 4 over 4. And this whole thing is evaluated from 0 to 2. So when we plug in 2, let's see what we get. So, oops, forgot my 2 pi. So it's equal to 2 pi, now let's plug in 2.
8 over 2.
8 minus
16 over 4. Which is 4.
4. 8 minus 4 is,
4.
times 2 pi is
4 times 2 pi.
8 pi. And we get 8 pi, yay, same thing. All right, so that's it.
Oh.
So calculating volumes, we did it 4 different ways. We found the actual cross-sectional area and multiplied it by the thickness and did the infinite sum that way. That's like how we started out doing all the way back with the pyramid.
Yeah.
Then we used the disk method where we cut it into discs and we just did pi r squared for our cross-sectional area.
Okay, we did this one every time.
Then we did the washer method where we, did I erase all my washer methods?
Yes.
Our washer method where we did the outer circle minus the inner circle. And then finally cylindrical shells.
Okay, we do this cylindrical shells every time.
There are cases where it's just easier to do it one way than the other. Going back all the way to the beginning, remember how I said you could think about calculating your area as an x times a dy or as a y times a dx.
Yeah.
And depending on your problem, it's just easier one way versus another way. This problem we solved using discs, and now we solved it again using cylindrical shells. We solved the exact same problem both ways. I don't know where the disc one is. Oh, it's right here.
But we didn't have to deal with.
So one way we did it with the disc, taking our slices this way. So we said our radius is y. We did pi r squared times dx. We evaluated the integral, we got 8 pi. This way we did our cylindrical shells this way.
Which ruined everything.
It didn't ruin everything, it just did it different. Multiple ways of thinking about the exact same problem. And oftentimes, thinking about one way is going to make the algebra much easier than doing it another way, which is a very useful skill when you're doing physics. Coming up with the right way to think about a problem, the easy way, the way that keeps the math simple. Okay, anything else? All right, give you guys the rest of class to start on homework.